Microsoft. Cool. Right, so yes, who am I? My name is Ilja. I am the Senior Director of Operating System Security at IO Active. I mostly specialize in code review, although I do other things as well, but I like low-level security stuff, mostly C, C++, assembly. In recent years, that has been supplemented by some Rust and a little bit of Go. I like operating systems, I like kernels, I like drivers, hypervisors, I like bootloaders and UFI and SMM and boot ROMs and embedded firmware and that kind of stuff, which I'm sure is shared by many here, because it is called hardwear.io. So, up like this, awesome, thank you. Okay, so the audience, I'm sure I have the right audience, but just to make sure, if you're interested in embedded stuff, if you're interested in firmware, if you're interested in bootloaders and boot ROMs and BIOS and UFI, this talk may be for you. More broadly, if you are generally interested in low-level security, you might like this. I have a little rusting at the end. So if you're a Rust nerd, there's a little surprise at the end. Or if you're just generally security curious or tech curious, there might be some nuggets here for you too. Before I move on, I kind of want to acknowledge I don't do this in a vacuum. I've learned an awful lot from these people and more. Some of them are at the conference, some of them may even be in this room. This is through papers and research and tweets and videos and trainings and conversations and DMs and so on. And I'm sure I've left out many, many more. But I just wanted to acknowledge that this isn't just me. I've built upon work done by many, many, many people over probably about a decade and a half, 2 decades. Right, so what's the agenda? I'll basically quickly go into the what and why of things, and then I'll quickly talk about some of the history and sort of where we currently are. And then I will dive into the review of one particular one. It was earlier mentioned that it's the one that Microsoft has created. I'll talk about the review I did, the timeline, the back and forth with them. And then I'll dive into some of the discovered issues. And once we run through that, we'll be more than halfway through. I'll talk about observations, a call to action, and hopefully I'll have a little bit of time left over. And if you have questions, I'll try my best to answer them, but I make no guarantees. Right, so what is an SMM Supervisor? Well, before we can answer that, is like, what is SMM? I'm guessing most people in the room know what it is, but roughly at the 50,000 feet view, it's this thing called system management mode, which is this very privileged mode that most software it runs has no clue it's there. It runs underneath them. It's kind of transparent. Sometimes it isn't. And some handful of pieces do know it's there, but generally, and certainly in the past, if you go back 10, 15, 20 years, it was certainly this thing that nobody knew about. It's gotten a lot more scrutiny these days because UFI's been UDK has been open sourced, and there's been a lot of security research. And the thing is, that thing is unbelievably powerful. It has access to everything. And that also gets us to what's a supervisor? Well, because it is so powerful, it gets attacked all the time. And there is an endless stream of SMM vulnerabilities that have come out in the last decade or so. And so we need a way to deprivilege this stuff, isolate it, measure it, and then apply policy to it. And there's a little blurb at the end, which is, I think from a blog post by the AMD folks that sort of roughly describe what your supervisor is. I won't go into all of it, but essentially it says, it basically takes SMM handlers, stuffs them in ring 3, puts a little ring 0 kernel at the bottom, creates a syscall interface, and then all of the privileged things such as I/O ports, MSRs, privileged instructions, certain pieces of memory, if it won't allow access to those anymore, so it stubs out code that touches those and replaces it with a syscall. And then it goes into this little privilege kernel at the bottom that runs in ring 0. And basically, ring 3 goes to ring 0 and says, hey, can you go do this for me? And ring 0 goes, I don't know, maybe. Let me check the policy. And the policy says, okay, yeah, you're allowed to do this. I'll go do this on your behalf. Or it looks at the policy and says, hell no. So that's kind of the what. The why is there's history here, right? This goes back a decade and change. Sort of around 2009, there was this really interesting research by Joanna and Rafael on the trusted execution technology, which is a thing from Intel about how to do like all these kind of things. And they looked at it and they said, well, okay, if your SMM handlers are compromised, this whole thing falls apart. And Intel said, yeah, you have a point, but here's what we're going to do. We're going to come up with this thing called an STM, which is an SMM transfer mode. And we're going to use a bunch of virtualization stuff. And we're going to basically use that to kind of isolate and deprivilege the SMM handlers. And it's going to be beautiful, and that's going to solve this problem. And when this paper was released in 2009, STM was a theoretical concept, wasn't created. But they were going to build it. And they did eventually, and we'll get to that. What was interesting is that, at least for me, that paper was sort of the floodgates as to, yeah, we need to look at SMM, and people did. And in the past 5 or 10 years or so, there has been like a steady stream of like SMM vulnerability, another one. It goes on and on and on. And the reason why is, as I said previously, SMM is really, really powerful. It is called ring -2 for a reason, right? And I'm assuming most people don't know what rings are, but if you don't, there's this concept that Intel has, and they didn't really come up with it. People kind of had the similar system before, but Intel basically said we're going to have 4 rings of privilege. The least privileged one is ring 3, and then there's ring 2 and ring 1, which nobody really uses. And then there's ring 0, which is where your OS and your kernel lives, and that's very privileged. And then they kind of added some things on. They created SMM, and they created extensions virtualization. So you got these negative rings, which is -1, which is the hypervisor. They got -2, which is this thing, SMM. And there's also the quote-unquote ring 3, -3, which is the management engine. But that is not something I'll be talking about in this presentation. But it's very interesting. So anyway, it's ring -2. It's real all the way at the bottom almost. It has an unbelievable amount of access. This is powerful stuff. This is stuff that nation states attack because they want to have bootkits and rootkits that are virtually undetectable and you can't get rid of, and you install the OS and they're still there. Like this stuff gets attacked by some very, very powerful adversaries. And the other thing is, TXT was one way, but it turns out there are other reasons why you want to attack SMM. One of the interesting ones that was presented, I don't know, maybe a decade ago at this point, was, and this has since been kind of sort of fixed in SMM, but it was this thing where if you can basically talk to an SMM handler from the OS and say, oh, hey, will you write to this piece of memory, which is not SMRAM, so SMM goes like, yeah, that's unprivileged from my point of view, but that's owned by the hypervisor, and so there were these attacks where you could leverage SMM to like break out of the OS to the hypervisor. And that's just one of many, right? There are a number of ways in which attacking SMM is very, very interesting, right? And so I went to the CVE website this morning, and if you notice that these are just CVEs from this year, and this is not all of them, there's more of this year, right? The list is very long, and it's Dell, and it's Lenovo, and it's AMI, and it's Inside, and it's Intel NUC, and it's everyone that builds software with UFI, creates their own SMM handlers, they're going to have vulnerabilities, and people are finding them, like, by the truckloads, right? And this stuff is really powerful, right? So this is terrifying. And you gotta go back, this list goes back 10, 15 years, right? It's long. Anyway, so the why of this is, we need something to control this because it's bad. Good news is there have been a number of steps even before the SMM Supervisor that have been taken. Right, from when people started attacking SMM handlers, we learned a lot. It turns out these SMM handlers were doing really, really dumb things. Because if you're living off in a corner and nobody's paying attention to you, you can get away with doing really dumb things. But once somebody starts looking, you're like, stop doing that, right? Don't put your fingers in the power outlet, right? That kind of stuff. They were doing stuff like taking pointers and storing them in non-volatile memory and stuff like that. So the OS could go in and overwrite those pointers, and SMM kicks in for some point and it's like, wait, this pointer isn't what I put there previously. Memory corruption, that kind of stuff. We've learned not to do this. The developers are aware of this. People have locked down page tables, so you can't do things like, oh, hey, I'm the OS, but can you please write to hypervisor? That doesn't work anymore. So a whole bunch of things have been done. On top of that, we've come up with at least somewhat of a list of here are stupid things you can do as if you're an SMM developer. And by and large, people have started applying these things and learning these things. And SMM code being written today is certainly a lot better than SMM code that was written 10 or 15 years ago. Although, as you can see from the previous list, it's not perfect, not by a long shot. There's plenty of bugs in SMM handlers. And so even though it's better now than it used to be, it's not good enough, right? And that's because this stuff is just so powerful. Everyone wants to attack it. The other side of that is that being a hardware firmware developer, certainly for SMM, if you're like that last mile kind of guy where you got to ship this thing out, but we've got this hardware problem, and you got a week to make this change to an SMM handler to work around hardware thing. Security is the last thing on your mind because you have to ship an actual piece of hardware, right? So that's part of the reason why this stuff happens. Thankless jobs there, people doing unbelievably amazing work, but in some of those cases, security is kind of the last, it's a priority, but it's priority 500 because priority 0 and 1 is we need to ship this stuff or we take, millions of dollars of losses for stuff, right? So that's not good. It kind of explains some of this. But ultimately what this means is we need more and we need better. And this is where the SMM Supervisor comes in, right? The idea is that you create a minimized SMM TCB, and you basically deprivilege, isolate, measure, and apply policy to all of these SMM handlers. And if you do that, and you go back to these lists, vulnerabilities will still be there, but these SMM handlers will no longer have the access they previously had, right? They would have very, very narrowly defined by policy, explicitly assigned and verified list of things they could do. Right, so now let's talk about current implementations. And this is actually not quite current, but this is the STM I was talking about earlier, where Intel in 2009 said, oh, we're going to do this, and then it was this abstract concept. They ultimately did create an STM implementation, and it was open source. It was put on GitHub. And then they said, we're not actually going to use it. We build it, but we're not going to use this. And then the thing they did build and use, which I'll talk about next slide, this is a few paragraphs from that paper. And these paragraphs talk about the history of the STM. And they talk about the capabilities and what it's supposed to do. And then all the way at the end, highlighted stuff basically says, architecturally, this was complete regarding the requirements that was in the last 3 paragraphs above that. But it turns out STM faced many implementation and deployment challenges stemming from inherent complexity. Because it turns out building a little micro hypervisor is really, really hard. So they're bad idea. Let's get rid of that. So the paper I'm talking about is this thing called Intel Hardware Shield Trustworthy SMM on Intel vPro platform. It's an awesome paper. It's only 6 or 7 pages. If you haven't read it, I recommend you do. It's action packed, it's dense. Take a weekend to read that stuff and go through it carefully because there's a lot in there. And read it a couple of times. But essentially, it talks about a mix of technologies that aren't quite an SMM supervisor, but have lots of parallels. And I'm summarizing here. There's a lot to unpack here for which I have no time. But essentially, these 3 technologies, Intel has named them runtime bias resilience, system security report, and system resource defense. And from a very high-level point of view, basically, runtime bias resilience is this thing where they lock down a bunch of the page tables and make use of some of the security properties on the memory that the memory paging provides. And then they made a few hardware tweaks and features that are very, very Intel specific that allow you to lock certain registers so that if you apply this to SMM, then even if SMM runs, it can't modify CR0 or CR3 and a bunch of other registers. And that is part of Intel Generation 8. System security report is part of Intel Generation 9. It was kind of a phased approach when this came out. And this facilitates attestation for these highly privileged SMM handlers. And basically, it was built in a way that it could safely attest SMM handlers, even if these super powerful SMM handlers are compromised, right? Not an easy thing to do. And it's definitely something I want to poke at some point, but I haven't yet. And then the last thing they added, now we get into Intel Gen 10. This is where they actually did the privilege separation. And so they have this thing called SMM entry, where SMM fires for some point. The first thing that happens is the SMM entry comes in. That runs at ring 0. It sets up the right environment based on the policy and so on. And then it basically goes to ring 3 and starts executing the SMM handlers. So at this point, the SMM handlers run in ring 3 and they're fairly unprivileged. That's Intel. So Intel isn't quite a supervisor, but it's similar-ish. There's parallels there. They try to achieve the same things. AMD actually built a full-on supervisor. And so what AMD did is they looked at the SDM that Intel proposed in 2009, and they said, we're going to do that. But they realized, let's not use virtualization for this because it's going to be a huge pain in the ass. We'll just do sort of the classic user kernel. We'll create a little secure kernel, run it in ring 0, and then push all the SMM handlers into ring 3. And that's exactly what they did, right? And so the idea is ring 3 enforces policy for MSR, IO, memory regions, privilege instructions, and so on. That is the current sort of state of where we are. There are, as I said, there are various levels of documentation. Intel one says that 6 or 7 page paper, which I would definitely recommend. There is also a bunch of patent filings from Intel that cover this to great detail, even more detailed than the 6 or 7 page paper. The problem with those is it's all written in lawyerese, because they're patents. They're not pleasant to read, but they give you a huge amount of detail. The AMD one, it's a bit of a sad state of affairs because we only have a handful of paragraphs in a blog post, fairly high level, a handful of paragraphs in a paper they put out, also fairly high level, and then a couple of paragraphs in a blog post on Microsoft, also relatively high level. I wish we had more detail on this. So the problem is none of this stuff is open source, right? It's all, there's a little bit of the Gen 8 stuff, of the BIOS resilience that made into EDK2, but everything else is closed source and we don't get to actually see it. We just have to take their word for it. So that makes it, I like to dig in and see what this thing really does. Makes it really hard to get a real sense how things work under the hood, right? It forces us to do, pretty intensive reverse engineering and runtime testing and fuzzing. And I'd love to do that, but I also have a day job. And this is multi-month efforts. So this is where the story gets, and I've been kind of looking at this SMM supervisor type stuff since late 2019, early 2020, and so for the past 2 years or so, I've been I want to see what this does under the hood. And then here Microsoft comes around and says, oh, well, we'll just build one and we'll open source it. And that's what they did, and it's available on GitHub. It's part of their Project Mu, which is this sort of modular adaptation of EDK2. I think they call it firmware as a service, which I'm sure is applied for their hardware, but I'm sure others can make use of it too. It's meant for a way to easily manage features, including security, and patches, including security patches. Although the security patches are kind of gated, so I don't get to see them. Some people in the room might, but I don't until they get published. But EDK2 security publishing, there's usually big timelines, and sometimes things get lost. It takes years before it becomes public. So I'm sure there's plenty of stuff I haven't seen yet that's been fixed. But anyway, that's a different story. the good thing is the SMM Supervisor by Microsoft is here. It's publicly available, and it's documented, and the documentation is really, really nice. The high-level blurb here from the Git repo basically says, this is the supervisor module for standalone SMM environment in x64. It's refactored Tiano Core common module and public portions of AMD SMM Supervisor module. I don't know what that means because there is no public portion of AMD SMM Supervisor module as far as I know when I looked. What's interesting though is there's a link to the AMD SMM Supervisor repo on the Microsoft GitHub page, but if you click on it, you get a 401 unauthorized. So it may be I'm sure it's accessible to folks at Microsoft, but it's not accessible to me. But I don't really care because their code is accessible to me, and so that's what I looked at. And what's interesting is that this code actually does reference this code actually does reference a bunch of AMD in several ways. So a number of the comments in the files will say, copyright so-and-so AMD. And so there's that one blurb that links to AMD. I don't know to what extent AMD was involved in this. I don't know if this was like a port of the AMD code and like Microsoft eyes or something, or if it was Microsoft basically not using their code but simply like being inspired by their supervisor. It would be nice to get some kind of clarity about exactly who owns what in there. But ultimately, I don't really care that much because the code's there and I can look at it. And so this is part of their documentation from a high-level point of view. The sort of stuff on the left here is what it used to be, and the stuff on the right here is the stuff that was changed that the Microsoft SMM Supervisor does. Right, in particular, right here, you'll see this is the little new secure kernel that gets installed fairly early in boot, and then these are the overwhelming majority of desktop handlers. All the green stuff is pushed to user land. It's deprivileged, and it's running in Ring 3. Right? So that's really, really nice. And I looked at code, and this is exactly what they do. It's nice. It's beautiful. Basically, my assumption was looking at this and basically saying, I'm coming at this assuming I have a compromised SMM handler. How do I attack the supervisor? How do I break it? How do I get in? Right? And so the entry points, or the sort of low-hanging fruit entry points that I looked at was basically, well, they keep talking about these syscalls. Let's go find these syscalls. And sure enough, there's a syscall entry.nasm, which is the kind of when the syscall comes in, like literally execution starts like right here, and then it saves a bunch of registers, and then here it calls it, and then off the slide it restores the registers and then jumps back to user. But that is essentially the like very low level assembly part of the syscall handler. And then, like, this guy is the actual C code, which is this guy. So this is like your syscall dispatcher. And then, there's some logging. But then basically here starts a relatively, and like obviously runs off the screen. But here it starts this relatively large switch statement of, syscall for I/O ports, and syscall for MSRs, and syscalls to get pages, and syscall for free pages, and so on and so forth. So that was really interesting. So I looked at that for about 2 weeks or so. Very interesting code. And I'll talk about some of the observations later on. But basically, my end result was I found about 9 issues in there, right? And this was if you know about. If you look at standard C code, this is like all the stuff that we've seen before. Right? It's inner overflows and race conditions and missing length and index validation, missing input validation, missing ACL-ish check, and we'll talk about that in a little while. The broken syscall stuff, which I'll talk about in a while too. More missing length checks or inconsistent length checks. And then a really, really interesting kind of sort of logic bug-ish with improper cleanup. The good news is, and this is all, it's all in GitHub, it's in issues. All of these things were reported to Microsoft. They fixed them, except for one, which is, I think it's the missing device validation, which is not fixed. But it is public. It's in. If you look at those two open, one of them is that device validation one, and basically that one isn't fixed. And the reason why is because A, it would be an awful lot of work to fix that particular one, and B, that is in profile code, which are not supposed to ship in this debug only. So it's kind of okay. The problem there, of course, is it creates technical debt if you don't fix bugs. And, of course, sooner or later, someone's going to ship this thing with this thing on, and it'll be a bug anyway. So hopefully someday this will get fixed. But at the present time, it's not, and it's kind of sort of okay. So I just look at time. I'll run to talk about some of these, but I don't think I'll have time to do all of these because I do want to get to my observations and call to action. But before I dive into details, the timeline here was essentially I did most of this work mid to late May up until very early June, and did a proper write-up with a bunch of details, sent it off to Microsoft, and then the folks at Microsoft the same day came back and said, this is really cool, we appreciate it, here's what we're going to do, we're going to lay out a plan. They sent me another email about a week later, providing updates saying we are actively reviewing this, and then talk about some administrative stuff like credit, should we do CVEs, kind of boring stuff. So I responded the same day saying, cool, awesome, acknowledged. Some time goes by, didn't hear from them for a month of change, so I go, let's ping them, see what's up. And so, hey, did you forget about me? And so a week and a half later, they mail back and they go, so sorry. By the way, this was not MSRC, because if you report stuff to MSRC, and if it's Windows or it's Office, it's great, they deal with it. If it's a Microsoft project on GitHub, response isn't always that good. I've had terrible responses there. So in those situations, I tend to just look at, like, who's the guy committing code? It's got an email address, great, I'm just going to email that guy then. And so that's what I did here. And so when I say MS gives an update, I'm talking about, like, a developer that works there that owns this code. So it's a little bit of a distinction. But essentially the guy was like, I'm sorry for the late response, but I was on vacation and I got COVID. And those are two good excuses, right? And then he says, here's the good news, all the bugs are fixed internally. So he said, what next steps? Basically, how do we make this public? How do we publish this? How do we document this? So we got back into, should we get CVEs? Should we not get CVEs? Ultimately, we're like, well, hardware hasn't shipped with this yet, so there's maybe not much of a point to get a CVE for this. So we're like, let's not do the CVE because it's administrative. It's an administrative hassle. I've had to do it before myself. I'd rather not. So I was like, let's skip that step. But let's make sure this is public, and it was. They gave me a list of suggestions, and I said, all of these look good to me. Whatever works for you. And about 2-3 weeks later, all this stuff they pushed to GitHub. They created issues for it, and then they created fixes for their own issues, and then they resolved the issues because the fixes were committed by them. And it worked beautifully, and I looked at them, and yeah, they're good. So with that, I'll jump into a couple of these. Probably not all of them, but so this is the first one. This is the image row flow, and this gets into the I/O port validation. And so this is it's called is I/O read write aloud, and essentially like it looks at policies, it enumerates policies, and goes, is this the I/O port? Okay, and then it does like, okay, is the I/O port plus size within the range of in my policy? It's got to be bigger than the beginning and smaller than the end when you define a range. And if it is, then it's allowed. Otherwise, if it's not in the policy, then it's not allowed. Problem is here because the address the size kind of it's translated here, but the address comes from untrusted user land. And so you see IO address right here, it's U32, and it's U32, that's U32. If I give you a really large address and you add a little size to it, that's going to overflow, right? So if it's really, really big, like 4 gigs and change, it overflows and goes back to 0, right? That's a problem, right? In particular, the problem is if you have a policy that says you are allowed to write to this a very low address. Then I give you a very high address that you're not allowed, but your validation goes, oh, it's a low address. Great. And so that I end up being able to, I will be allowed to write to high port when there's a policy that only says you can write to this very low port. That is a very specific set of circumstances. It highly depends on specific policy, but it is definitely above. And it was fixed. That's one. The other one is this race condition, which is kind of cute. So there's this handler GUID, which references something. And this pointer points to userland. It's been range checked before, so it's in range, it's valid. But it points to user, which means this can be asynchronously changed, right? You can do async IO or async DMA or something, and you can get these things to change. And so there's this cool thing here where they go, okay, compare this GUID to something, and if it's this guy, then do this. If it's that guy, different GUID, then do this. And then all the way at the end, there's some cleanup where they say, okay, if it's this particular GUID, then free this context that was created right here. The race here is basically that when it compares here, I can have it not match. And when it compares here, I can have it match. And what that means is I am now freeing this thing that was created here, except this code path never happened because at this point, this GUID didn't match. So you are now freeing a context pointer that doesn't point to heap, which obviously is a bad idea. It's a classic time check, time of use. The result is basically, yeah, you're freeing a resource that isn't necessarily on the heap, which can have really bad consequences. Yeah, there's another one where this is a trivial one, which is so this context and context size are defined by user. Like user can say, here's 1 byte or here's 100 bytes. What you'll see is there's an assert that says, I assert that it must be this size. The thing with these asserts is that they are developer asserts, right? This does not ship in the release builds. So this assert goes away, and yet it touches a bunch of stuff where it goes like, oh, it must be there, except if this assert is no longer there, there's no length check, and so this could point out of bounds. It could crash. You could end up touching a kernel page. You may be able to induce what's on there, so that may give you some kind of information leakage. What's interesting is that whoever wrote this quote was like, we should assert for this, but didn't go, actually, we shouldn't make an assert. It should be something that is also there in the release book. It's one of these pet peeves for me, which is doing bound checks and asserts is something that is doing bound checks and asserts is one of these weird things that I see way too often. Yeah, this one is an interesting one. So you go straight up in the syscall handler, and you see this argument 2, and that basically is a CPU index, and they index into an array, and they write stuff to it. Obviously a bad idea because it's not validated. That is straight up memory corruption, and it is one of these, write anything anywhere primitives, write almost anything anywhere primitives. So this is bad. I highly suspect this is going to be very exploitable. And I'm not going to dive into all this, but the problem here is that, so this is the next issue. This device is provided by, the content is provided by userland, and it's actually, if you dig into this function, it's a really complicated structure that has like forward references with a bunch of lengths, and there's other content there that needs to be validated, and this function basically just assumes that the content has already been validated, and it hasn't. So all sorts of bad things happen. And this is the one bug that hasn't been fixed, by the way. The fix here would be to basically re-implement this thing and add a whole bunch of bound checks. It gets pretty complicated. Which I suspect is the reason why they didn't fix it is because it's so much work, and it ends up that one is profiled for only. Let's see. Yeah, the register unregister is interesting. So there's 2 system calls. One is to register another SMI handler in userland, and the other one is to unregister an SMI handler. The thing is, even with the SMM Supervisor, it is still possible to have an SMI handler in kernel. They're just very rare. Probably for some system ones, but if it's like a third-party one or like not one that's part of EDK2, it should be in user. What's interesting about this one is so when you look at the registration, you see this false flag that's set, and that basically is this is supervisor handler flag, and that means so it won't be set, so it'll be false, which means anytime user registers an SMI handler, it's explicitly marked as not a supervisor handler. Problem is when you unregister one, because you get a handle back to this registered handler. When you unregister it, it goes through its table of handlers, and it says, "Oh, the ID you gave me for this handler is there. It's in the list. I'll go and register it." There's no check to see if this comes from userland, and if it comes from userland, then it shouldn't be allowed to unregister kernel SMI handlers, right? Except that check is not here, so userland can just go like, "Oh, you know those two highly privileged SMI handlers that are still in kernel? Yeah, I'm going to unregister you for you." Yeah, okay, I'm going to skip, I'll do this one and I'll skip through the rest. This one I think is interesting. This is one of those classic ones. So this is the assembly I showed earlier that basically does the actual syscall handler. This is stuff that gets called immediately, even before the C code. And what you'll see is this saves the user registers, and then because kernel is going to reuse these registers, you have to save them. And then once you're done, you have to restore them, because otherwise the user gets to see what kernel registers were. And even disregarding the security consequence, your user caller kind of probably has a dependency on these things, so you have to restore it, right? That makes sense. Except, there are more registers in Intel than just these. That's a problem. In particular, MMX, SSE, FPU, and I didn't really see any FPU instructions being used, so FPU is probably not that big of a deal. But especially like the SIMD instructions, optimized compilers tend to use those to like optimize things like memcopy and so on. So there's a chance that there's a memcopy happening somewhere in kernel to copy a bunch of data around, that some of that content ends up lingering in one of these registers, and that then ends up leaking to user, which obviously is a bad idea. Anyway, yeah, I'm going to skip through a bunch of these because I have about 5 or 6 minutes. There you go. Okay, there we go. Observations, right. So I think we ran through maybe 2/3 of them. But essentially, this code is written by very, very experienced, very senior developers. If you look at the code, you see it's high quality. If you look at the documentation, you will see that this is written by people who know what they're doing. Like, they're doing the right things, they're highlighting the right things. They understand their attack surface, they understand the risks, they know what they're doing. All the issues I just covered, and the ones I didn't, they're one-offs, they're not systemic, right? For, like I had one missing index in there, all the other indexes were checked, right? So it was literally just like an oversight. But yet, these 9 bugs did happen, right? Why, right? Drum roll, because it's written in C. It's just, I mean, we've had 50 years of it. It's been very useful to us, but it's led to tens of thousands of security bugs, including these 9, right? So I had a little Twitter exchange with David Weston at Microsoft, where he commented on something saying, well, writing perfect SMM code in C is a good goal, but probably not attainable. And so one of the things you should do is sandbox your SMM handlers to contain vulnerabilities like this. And I tweeted back to him and said, writing perfect sandbox SMM code in C is a good goal, but probably not attainable and practical. Which, it wasn't. So basically, and this gets into my call to action, right? I think, as I said, C has served us very well for 50 years, but it's time for it to go and die, right? I'm not joking. Like, it's okay for legacy. I don't expect all C code to magically be ported to Rust or something else. That's an impossible task. But if you're writing new code, don't write it in C or C++. Please don't. We have better alternatives now. I like Rust. That seems to be the trend. You don't have to do it in Rust. There's other languages. V looks very interesting to me. You can do some of this stuff in Go if you really want to, but the runtime gets in your way. Anyway, Rust seems to be kind of the trend we're going to, and I kind of like it. The good news there is, if you're doing writing stuff for UFI, that is starting to kind of happen a little bit. It's still early days, though, but there are some Rust implementations for EDK and UFI. The thing is, EDK2 itself doesn't currently have bindings for this. I hope they do. So this guy works at Intel, and he did a presentation about this 2 or 3 years ago, and this is kind of his proof of concept. So it can be done. Those bindings are there in this staging tree. The problem is the staging tree hasn't been touched in 3 years, and it's not EDK2. So I would really like to see some movement on this, especially given that the Linux kernel is about to support Rust. The dwrite stuff in Windows was just ported to Rust. Like, this stuff is happening, and I want to see this happen in UFI as well, right? And if it's in UFI, that means our supervisors can make use of it too. And the problem is this, right? Chances are, if we don't do this, if we keep doing this in C and C++, it's not going to end with these 9. There's going to be more, right? So one last point here is that Rust is not a silver bullet. You can have security bugs in Rust, and there have been security bugs in Rust code. What it will do is it will drastically reduce the number of security issues of this kind if you're writing in Rust. Some of the bugs I covered here would definitely be caught by Rust. The unvalidated index stuff, Rust would have caught it. Some bugs it probably wouldn't have. This gets more into like the logical side of things, but it would have drastically reduced the number of bugs. Last call to action. This is my last slide. I think I don't know me on time. I got 2 minutes. Great. So basically, the other call to action, which I haven't even talked about in this presentation, but this is something I suspect is going to become a problem, is the policy, right? The actual policy that gets enforced gets set or will be set by the actual hardware vendors, right? The individual BIOS vendors, HP, Lenovo, Dell, AMI, Inside, Intel, so on. They're going to set these policies. My guess is the first set of policies we're going to see is either going to be a very, very small deny list or an unbelievably large allow list, right? Which is an allow list that allows everything, at which point the supervisor becomes useless because it just allows it. So towards the future, I think the policies are going to be a thing we have to look at. We're going to have to audit these policies, and we're going to make sure that they are restricted to just what we want to allow and nothing else. And with that, that's my presentation. I thank you so much for listening. Any chance we have time for like one question or something?
Yes. First, big round of applause to Ilja. And I think we can sacrifice 1 minute of coffee break for one question, right? We have one.
So thanks for the presentation. How did static analysis, in your discussions with Microsoft, how did static analysis figure into this whole equation?
Good question. It didn't in this case, because I was all manual code review. In general, I am a big fan of static analysis. I think it would have been helpful here. I didn't think of it because it's, we're kind of in the zone when you're like focused and stuff. I was just reading code. If this was a more intense, more thorough, full review, I would have absolutely applied static analysis. Big fan. It just didn't happen in this review.
Okay, perfect. Thanks everyone. Another big round of applause to Ilja.
Thank you for listening.